Okay, so my name is Michel Quintard, and I'm going to talk about multi-scale analysis of transport phenomena in porous media. And in a previous chart, I just introduced the idea of multi-scale description, and I introduced the idea that we can develop nice modeling if we assume there is some sort of separation of scale, which is reminded here. The small scale of the system here is much smaller than the large scale of the problem we are interested in. And there is some intermediate scale at which I can develop some macro scale variables. So let us take the example of a fluid flow, which is characterized at the pore scale by pressure and velocity. And typically, if I look at the pressure, the velocity field at the pore scale, I have something like that. I have some sort of local Poiseuille flow, if you want, with a zero velocity on the fluid-solid interface and the velocity, large velocity in the center of the constriction. This is an illustration of the difficulty of solving directly at the pore scale transport phenomena in a system which is very large, and therefore this is the motivation for an intermediate description, which requires the development of a macroscale variable. Macroscale variables can be defined in many different ways, and I'm going to use today just a simple illustration by saying, well, why not just looking at the average of the small scale velocity, and will be defined. There are much more complicated definition, but I'm just going to use a very simple one. So this is just the volume average of the velocity over the volume of the fluid phase divided by the volume of the averaging volume, which is represented here. And the interesting feature here is that if I have a nice separation of scale, now the velocity field here actually is a much simpler field, much more tractable in terms of modeling, because here it's becoming locally uniform, and therefore I have a very complicated field at this scale, and I have a uniform field here at this scale. And for instance, if I have an injection well, for instance, I can calculate a flow in the system, assuming I have for instance, an exit well here, and those fields have a characteristic length which is much larger than this one and makes things tractable. This is just an example, and this is important to understand that there are many ways of defining those macro scale field variables, here pressure and velocity. So I talked about volume averaging. There is another technique which is quite useful when we are dealing with a natural system which are naturally heterogeneous. And one possibility is just to think of that in terms of a realization of an ensemble, a stochastic ensemble. So I imagine I have one realization, and I imagine I have another one, and then a bunch of realization, and therefore the macroscale variable, well, could be defined by the expectation of the variable here at a given point. That's another definition, and this is very useful because if you look at a real medium, for instance, it looks that the heterogeneities looks like some sort of random process. There is a link between the two. And the link essentially is due to the fact that I have a single realization. I have one aquifer, one reservoir, and therefore I have to define some statistical properties. And most of the time I use ergodicity, which means that I have the statistical properties here I define by spatial averages over a single realization. And there is another technique which is a little bit different, and that looks at the solution of the problem by these are not exponents. These just are indicating the V1, a typical velocity field, and another one. Epsilon is a small parameter which is here mostly characterized by the ratio L over capital L. And the idea is that actually the capital V will be obtained by looking at the process and making the small parameters go to 0. This is called homogenization theory, the framework of asymptotic description. These are ensemble averaging and these are volume averaging. Those three definitions actually defines the most important three classes of upscaling techniques for the analysis of porous media transport phenomena.